Now I've rewritten the rotation matrix here. We put in our value for our x0 and y0, so these are just the points on a circle, and this is the x coordinate of a point and y coordinate of a point. Now in order to rotate that point round to a new point x1, y1, we multiply it by this rotation matrix. Now we're not just going to rotate it once or twice, we're actually going to rotate it. In our example here, we'll rotate it 8 times. So that means that we're going to have a counter. So the counter is going to count the number of rotations. So we'll put the counter as I, and we'll start off with I being equal to the value of 0. So 0 is the first rotation, and 1 is the second, and 2 is the third, and so on and so forth. And there's a reason for doing it like that, which we'll see when we look at the mathematics. So it means that the x to the I plus 1 and y to the I plus 1 is equal to the rotation matrix times xi, yi. So for example, if you were looking to get the 7th rotation point, so you would have x to the 7, y to the 7 would equal the rotation matrix times the value that you got for x to the 6 and y to the 6. So you can see here it's going to be this iterative process. Now there's one major problem we have here, and that is that we want to be able to rotate the point around a circle in order to synthesize the basic trigonometric functions. But the actual rotation matrix that we have here contains the basic trigonometric functions. It already contains sines and cosines. So we've got a kind of chicken and egg situation here. We're trying to synthesize the basic trigonometric functions, but in the process we already have to know what the basic trigonometric functions are because they're inside our synthesizing method. So we really need to transform this rotation matrix so it doesn't contain any trigonometric functions. So I've put a little question mark here, and if you want you can pause and see if you can try and work out how we're going to rotate the points on a circle using a rotation matrix that doesn't contain any sines or cosines. Now I'm not suggesting you're going to get the answer to that, but it might be worthwhile sitting down for 5 minutes and having a little think about it. So also when we build the digital circuit, because that's the direction we're going, we're actually going to build a digital circuit that will synthesize this, or it will mimic the rotations. Now the digital circuit can only perform very basic arithmetic, that is plus, minus, multiplication and division. So a rotation matrix can only contain these basic arithmetic elements. So we're wanting to replace these complex functions just by simple additions, subtractions, multiplications and divisions. And that's what we're going to look at in this video. So just to give you a little start, what we want to do is try and get rid of these functions here and replace them with simple arithmetic manipulations. So here's a direction that we can go in. We can take our matrix here, and if we like, we can take out a common factor. So let's say we take out the common factor of the cos theta. So if we take out this cos theta, it's going to leave a value of 1 and 1. So right away we've got rid of some of our complex functions. We've got rid of the cos theta within the matrix. And of course the other factor here, minus sine theta, would become minus tan theta, because we can write tan theta is equal to sine theta upon cos theta, and there is the little proof there, because sine theta is y upon r, cos theta is x upon r, and when you divide these out we're going to have y upon r times r upon x. Those will cancel out, we'll get y upon x, which is just the tan theta. So that means we can rewrite this matrix in this little simple form here. So let's go ahead Now, and we're going to have a closer look at the tan function, because we want to get rid of these functions here, the minus tan theta and the tan theta. Now we also want to get rid of this cos theta as well. So let's continue with the rest of the video and we'll see how we're able to get rid of these complex functions. So before we go on to the graphical calculator, I've drawn out a small section of the tan function. And the matrix that we have down below, we're interested in these terms here, the tan theta and the minus tan theta. So the theta term is along the x-axis here, and the tan theta is going to be up this axis. So let's go ahead and we'll have a look at this in the graphical calculator. So this is one of the key points of the CORDIC algorithm, and it's a neat little bit of mathematics. So we've drawn out the tan function here, so let's just zoom in. Now we've got the angle theta along the x-axis and tan theta along the y-axis, and you'll see we've got two sets of numbers here, one in blue and one in pink. So we're going to start off with the little pink values here. Now we decided that we were going to rotate the point around 45 degrees, and then we would half the 45 would give us 22.5, and then we would half that angle and we would keep halving it. So we can do that if we look at the little pink values here. So you can see that in the first instance here we've got 45 degrees. I've also written it in radians, and we can see that the tan of this 45 degrees is equal to 1. So the tan of 45, so this is a 45, is equal to 1. So you can see we've got pi by 4, which is 45 degrees, and the height is 1. And we're going to move it down to the next position. The next position would be, I'll put this position here, and it would be 22.5 degrees, and the tan of that is 0.414. So the height here is 0.414, and we can continue doing this for each of the values along this tan function all the way up to the 8th value. Now, actually the 9th value, because it starts off at a value of 0. So now if you want to, you can open up this simulation in the resources section and have a little play with it yourself. But what we note here is that along this axis here, the numbers that we have, they're not easily generated on a digital circuit, which is going to use purely Boolean logic. So we're trying to generate these numbers here, which is they're going to be, for example, 0.414213 or 0.1989 or 0.0098, and so on and so forth. So we're looking at the bottom line here. But there's nothing to stop us from using a different set of angles. So we don't need to rotate by 45, then 22.5, and then 11.25, and so on and so forth. We can choose a different set of angles, and all we need to do is to make sure that we choose angles which are either a little bit more than half or a little bit less than half, as long as we're consistent with each value that we choose. So for example, if we look at the values here in blue, what we've done is we've chosen the values here along this axis, which is the tan theta axis, and you'll notice that the value for the tan theta is a value of 1, which is just the same as the original one. But now, whenever we move it down this axis, we're not moving it halfway, we're moving it just a little bit less than halfway. So the originally we were going to move it from 45 to 22.5. Now we're going to move it from 45 to 20, this 26.565. So why are we moving it to this angle? Because at this angle here, the tan of theta is exactly a half. And if I go to the next value here, we're going to move it down such that the tan of theta is now a quarter. And then it's going to be 0.125. It's going to be 0.0625. So you can see here that these numbers here are very easy for us to generate on a digital circuit. So you can see here that what we're actually doing is dividing the tan theta by 2 each time. So we started off at a value of 45 degrees, which gave us a tan theta of 1, and then it went to a half, so that's division by 2, and then we divide that by 2, and that by 2, and so on and so forth. Now it's very easy to produce a division by 2 on a digital computer. It's done simply by shifting to the right, and we'll show you that in a different video. So it means that we can replace the complicated function tan theta with a very simple bit of arithmetic. And we'll have a look at that in just a moment, but I do suggest you open up this file in the resources section and have a little play with it and take your time and think over what we've just talked about. So let's go ahead and we'll have a look and see how we can now adjust the matrix to get rid of the values of tan theta. So we can replace the tan theta and the tan theta here with the simple arithmetic manipulation 2 to the minus I and 2 to the minus I. So don't get confused here. All we're doing is taking the tan theta, which is up this axis, and we're allowed to choose the values for that tan theta, and we've chosen the values of that tan theta to be the values of 1, and then 1 upon 2, 1 upon 4, 8 and 16, and so on and so forth. And those values are then going to be 2 to the power of 1 upon 2 to the power of 0, 1 upon 2 to the power of 1, 2 to the 2, 2 to the 3, 2 to the 4. Now, 2 to the power of 0 is just a value of 1. So that's just 1 upon 1, which is 1. And that's why we started off with I at the value of 0, and as opposed to I at the value of 1. So it means that we can rewrite this here as 1 upon 2 to the power of I. And again, that can be written as 2 to the minus I. And I is just the number of rotation. So 0 is the first rotation, 1 is the second rotation, and 2 is the third rotation. So that means we're another step closer to getting rid of all of the trigonometric functions in order to produce our rotation. The only thing we have to get rid of now is this cos theta. So let's look at that in the next page. So we have our rotation matrix here, and we multiply that by cos theta. So let's look at an example. If we were to go from a point x0, y0 to a point x1, y1, then we would have our rotation matrix, and we would multiply it by cos of the angle theta 0. And the rotation matrix would be given by 2 to the minus 0 and 2 to the minus 0. Now if we were then to go from the original point x0, y0 to the new point x2, y2, then it would be an iterative process. That is, we would rotate first of all via this rotation matrix, and then we would rotate by the second rotation matrix, which would be 2 to the minus 1 and 2 to the minus 1. But note what happens to the values for our cos theta. They get multiplied together. So we would have cos theta 0 times cos theta 1. So if, for example, we were to have 9 rotations, then we would have a value for this multiplicative value, which we call k, and it would have the 9 values associated with it. So it would be cos of theta 0 times cos of theta 1, cos of theta 2, all the way up to cos of theta 8. So the actual multiplication value is just going to be a constant, and the constant is going to be determined by how many iterations or rotations that you actually produce within your algorithm. Now, there is a simpler way of generating this value for k, which uses just some simple algebra, and this is the process that we use in order to generate this value of k. So if we were to say k of n, so n is just the number of rotations, it's going to be the multiplication, so that's the sign for multiplication, of each of the ki values. So I runs from 0, 1, 2, 3, 4, and so on and so forth. So it's going to be the multiplication from I equals 0 to n. Now in our case, n would be 8, so it would be going from 0 to 8, which would be 9 iterations. And that's the multiplication of 1 upon the root of 1 plus 2 to the minus 2i. Now, I'll prove this in the next page, but for the moment we can just accept it. So we have a simple way of generating the value for our constant multiplication factor k. Now, if we were to allow the value of n to tend off to infinity, then the limit as that n tends to infinity, or our value kn, is going to be approximately equal to 0.60725,293, so on and so forth. So what we have now is a simple way of generating all of the information that we need without having to revert back to any trigonometric functions. So we simply have a constant for k, and our tan theta is replaced by 2 to the minus I. So finally, we can write out the algorithm as x to the I plus 1 and y to the I plus 1. So those are the values for our final position after rotation, is given by the initial point on the circle xi, yi, and we have to multiply it by our rotation algorithm. But note here, we have to be careful because we can rotate the point either clockwise or anti-clockwise, dependent on whether the value for y is positive or negative. So we change the direction of rotation by changing the sign of these two values. And we can do that simply by putting in a value of d. So d tells us whether we're going to rotate the matrix in a clockwise direction or an anti-clockwise direction. And we can say that if y is positive, then d would be minus 1, and if y is negative, then d is equal to 1. Now, one further thing we have to do is actually pull out the value for our angles. So we've seen previously that we pulled out the value for our angle by adding or subtracting on the values of the chosen angles, for example, our 45 degrees or our 22.5 and so on and so forth. So we generate the next value for the angle. So this is the approximation for the angle, and it's given by the previous approximation for the angle, and we're going to subtract off the value di e to the power of I. So di is just going to tell us whether we actually subtract or add, because it will be a value of minus 1 or 1. And e to the power of I is simply our set of angles, and our set of angles are given by arctan 2 to the minus I. So this is the final algorithm that we've been working towards. Now, it might be difficult to see how this all holds together and works from the mathematics, but don't worry too much because we will be going on in the next video and looking at an actual example in the graphical calculator. So what we want to do is just prove this little identity here, and we'll go and do that on the next page. So we said we can generate cos theta from this simple arithmetic manipulation, and it's 1 upon the root of 1 plus 2 to the minus 2i. So we know that the values that we're going to use for our angles are going to be given by 2 to the minus I. So 2 to the minus 2i is in effect the square of that value. Okay, so that's going to be equivalent to our tan squared. So then we have to work through the identity and prove that one side is the same as the other. So we can say that if we were to square both sides, then we would have cos squared theta as 1 upon 1 plus tan squared theta. We can rewrite the value of our tan squared theta as sine squared upon cos squared. We can take the common factor here of cos squared on the bottom, and we're left with cos squared plus sine squared. Therefore, we can say that our cos squared theta will be 1 upon, and this identity here will just be a value of 1. So 1 upon 1 plus cos squared, so we'd have cos squared would equal cos squared, and we can take the square root of those and we would simply we'd get back to our value of our cos. So this identity does work, and that's the little proof of it. So this has been a long video, and it's been quite mathematically involved. Don't worry if you haven't understood all of the mathematics. We will be going through a simulation on the graphical calculator in the next video, and this will help to cement your understanding. So we've generated an algorithm here that will allow us to work out some trigonometric functions, and we've generated it in such a manner that it's very easy to create a digital circuit that will emulate this or synthesize this algorithm. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.